Honorable,
warahmatullahi wabarakatuh.
Honorable Assistant Professor of Mathematics from Mathematics Department of King Faisal University, Saudi Arabia, Kinda Abu Asbeh, PhD. Honorable, the Dean of Faculty of Science and Mathematics, Diponegoro University, Professor Dr. Widowati, SSE, MSc. Honorable, the First Vice Dean of Faculty of Science and Mathematics, Diponegoro University, Farihin, SSc, MSc, PhD. Honorable, the Second Vice Dean of Faculty of Science and Mathematics, Diponegoro University, Professor Dr. Kusworo Adi, SSc, MT. Honorable, the Head of Mathematics Department, Dr. Susilo Haryanto, SSc, MSc. Honorable, the Secretary of Mathematics Department, Dr. Titi Ujiani, SRRM, MSc. Good afternoon, ladies and gentlemen. My name is Aisyah Siofi Gunawan. It's a very precious chance for me to be the Master of Ceremony for today's visiting lecture with the topic of topological space. Before we start, I would like to read the procedures and instruction for the forum, which every participant must follow. First, please take your comfortable seats and prepare your paper and pen to take notes. Second, participants are required to attend the entire agenda of visiting lecturer 2021. Third, participants can only turn on their microphone on when allowed and must turn the microphone off during the whole event. Fourth, please hold all questions until the question and answer session. And to ask questions, participants may use the raise hand feature or send the question through the chat box with the format name_batch_question. For example, Aisyah Sulfi Gunawan _2019 the question. Participants who's going to ask questions are required to turn on their camera and microphone, then introduce themselves before asking the question. Fifth, participants are expected to turn on the camera during the photo sessions and the closing event. Participants must fill, and lastly, participants must fill the attendance link of all of the event that will be sent in the chat room by the operator. Okay, next, there will be some words from our Dean to Professor Dr. Widowati, SSE, MSc. We welcome you to the stage.
Thank you very much for Master of Ceremony, Ms. Aisyah Sulfi Gunawan. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Excellency, Kinda Abu Asbeh, PhD from King Faisal University, Saudi Arabia. Thank you very much for your joining in this event. Excellency, Farihin, PhD, as a Vice Dean for Academic and Student Affairs of the Faculty of Science and Mathematics, Diponegoro University. Honorable Dr. Susilo Haryanto, as a Head of Mathematics Department, Faculty of Science and Mathematics. Dr. Titi Ujiani, as a Secretary of Mathematics Undergraduate Program. And also Ratna Herdiana, PhD, as a Moderator. Dear lecturer at Department of Mathematics and all participants. On behalf of the Faculty of Science and Mathematics, I have the great pleasure to welcome all participants of the visiting lecturer events. The aim of this visiting lecturer is in line with the goal of the Faculty of Science and Mathematics to facilitate brainstorming and state-of-the-art information in fields of the science and mathematics and also its applications. As we know that the vision of the Faculty of Science and Mathematics is to become an excellent research faculty with international reputation in the field of science and mathematics, as well as the development of its application. As a faculty with international reputation, of course, students of the Faculty of Science and Mathematics certainly highly competitive at the international level. The excellence and international reputation are the key achievement goal of the Faculty of Science and Mathematics vision. It means that the governance should be based on the international standards. As for one of the way to achieve the key goal is through visiting lecturers. My sincere gratitude, especially to Dr. Kinda, who will be today's speakers, and to all participants for their great contribution in promoting science and mathematics for Diponegoro University Academia. In addition, for today's lecture, the topic of the material is topological space. I think that today's topic is very relevant, especially for all students and lecturers in Department of Mathematics. I want to use this opportunity to congratulate the head of Mathematics Department, lecturer, and also student for their foresight in choosing the best lecturer. I do hope this visiting lecturer events can inspire many scientists to improve their research and open international collaboration between Diponegoro University and King Faisal University.
I hope so.
Finally, by the grace of God Almighty and consent of all participants, on behalf of Faculty of Science and Mathematics Diponegoro University, I am as a Dean hereby announce that online visiting lecturer event with the topics topological space is open.
Firstly, can I start?
I encourage all participants to participate actively in the interesting discussion. Enjoy your lectures. Thank you very much for your kind attention. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Okay, firstly, I just want to thank you for giving me this opportunity, and it's my pleasure to join you as a visiting lecturer. I hope this will be effective and give passion, give new experiences for all of the attendees. Thank you very much. And I'm trying to, okay, it's a work.
I'm sorry, Dr.
Yes.
Kinda.
Yes.
We have not started yet.
Okay.
We will, yes. The MC, can you continue? Unmute your mic, please.
Okay, thank you, Prof. Widowati, for the remarks. Now we can move on to our main event today, that is lecture from Mrs. Kinda Abuasbeh, PhD, with the topic of topological space. But before we welcome our lecturer, I would like to introduce our moderator first. To the operator, share our moderator CV, please. Okay, our moderator for today's lecture is Mrs. Ratna Herdiana. She took her education in University of New South Wales, Sydney, Australia, in mathematics, and took her PhD in University of Queensland, Brisbane, Australia. And she has work history. The latest is working in the Department of Mathematics, Faculty of Science and Mathematics, Universitas Diponegoro, Semarang, Indonesia, and has a lot of publications. The latest publication would be stability analysis of tuberculosis and epidemic model with nonlinear incidence rate and treatment effects in 2021. She also have conferences paper, which is some of them are Moodle as a tool to manage probability and statistics course in University Technology Petronas, presented at the International Conference on Engineering Education, or ICEE, on July 2008, and variable step size implementation of the balanced Milstein method for stochastic differential equations, presented at the ICIAS on November 2007. Okay, without further ado, let's just welcome our moderator, Mrs. Ratna Herdiana, MSc, PhD. Mrs.
Thank you
Ratna?
very
Okay.
much. Thank you very much, the MC, Ms. Aisa Silvi. Wonderful introduction. It is a pleasure for me to accompany Dr. Kinda, our special guest today, to be the moderator of this visiting lecture program. It's a series. We will have another one on Friday. I would like to greet our distinguished guests, especially the faculty dean, Professor Widawati, the vice dean, fellow colleagues in the Department of Mathematics, and of course our enthusiastic students. Assalamualaikum and greetings. Warm welcome to all of you here. Our visiting lecturer today is a young mathematician. She's very young. Dr. Kinda Abusbeh, a PhD. So before we listen to her lecture, first let's have a look at her profile, a brief CV. Can the host share? Yes. So her full name, Kinda Abusbeh or Jauda, PhD. She's now assistant professor in mathematics at King Faisal University, Saudi Arabia. Her research interests general areas of control and stochastic optimization and fractional differential equations, or FDEs. More specifically, working on Kalman filter and sequential FDEs. Her academic education background, she completed her PhD in mathematics 2018, so not long ago, from University, Eastern Mediterranean University, Famagusta, Northern Cyprus. That's in Turkey. So.
Yes.
Her Master of Science in Mathematics, she completed 2012, Bachelor of Science in Mathematics in 2009, both from Al-Najah National University, Palestine. Her work experience, professional experience, she's now assistant professor at the Department of Mathematics in Faisal University since 2019. Before that, she was assistant professor at Arab American University, Palestine for 1 year, assistant professor at Gurney American University also for 1 year. She also has experience as lecturer at King Saud University, Riyadh, Saudi Arabia. She's also active as a member in editorial board, online mathematics journal. Courses that she taught is mostly analysis subjects, real analysis, functional analysis, stochastic calculus, complex analysis. This is called, I think, difficult subjects.
Yeah.
Yeah. Public publications. Recent paper published in reputable Journal of Mathematics 2021 with the title Psychoputo Logistic Population Growth Model. Also in Journal of Statistics, Applications and Probability, the paper titled Population Growth Modeling via Rayleigh-Computo Fractional Derivative. And she has many more publications with her research group. The latest submitted article is a fractional epidemiological model for bone remodeling process. Will be published in AIMS Mathematics 2021. Okay, that is the brief CV of our guest today. And now her topic is on topological spaces, which for most students maybe is a difficult subject, but don't worry, yeah. Dr. Kinda will try to start from the basics, yeah. So you need to follow from the start, yeah, students, so that you don't get lost. Okay, Dr. Kinda, you have until 5 p.m. or 1 p.m. Saudi time, I think. Yes. Then we will have the 30 minutes discussion or question sessions. But feel free, Dr. Kinda, if you want to ask questions to the audience during the lecture. So to be more interactive, if you want. Yes.
Okay.
Yes. So during the lecture, participants can also post a question in the chat box. Yeah.
Okay, I will try.
Okay, now so the time and screen is yours, Dr. Kinda. You can start.
Thank you so much. Okay. Okay. So the topic that I will introduce today is a topological space. We'll start with why do we need topological spaces, and then to start from a background which is known for the students of mathematics for sure, which is the real analysis, then start one by one to enlarge the skills and the information that we have from the real analysis up to reach the meaning and the definition and the details and the behavior of the topological spaces. We will end up with some properties of the topological spaces, important properties of the topological spaces. Let me just, I'm trying, okay. As introduction, as you know, mathematics generally can be divided, let me say, for three main parts, which are arithmetics and algebra and geometry. From those three main parts, we can go through lots of parts, lots of fields of mathematics. One of those fields is the topology. I don't know, one of those fields is the topology. Now, what is topology? Why do we need topology? And what are the things that the topology is concentrating on? Mainly, we can start by connecting the topology with the geometry. Geometry is studying or concentrating on measuring the quantities of let me say of properties or concepts that considering the quantities mainly, but from the other hand, sometimes we need to study the quality of let me say, some concepts of the space. Topology concentrate on this issue, which is studying the qualities of spaces and what those qualities will give me properties after that. And those properties, how do they affect the behavior of the space that we are working on to reach, always in mathematics, we are trying to reach an ideal case, to reach an ideal space which serves and keep or give us the theorems, the good theorems and the good results that we need to work on. At first, we can consider this question. If we have, for example, a space, we may ask, is the space connected? In fact, geometry or other types of, or other parts of mathematics, they will not answer such question in the perfect way. Topology will answer this question in a perfect way to give us a description of the connectedness property and how can we manage or how can we investigate this property and what do we have results after having this property valid in the space. For example, we can say if the space that we have is connected, then we will have lots of theorems that will be valid, and lots of theorems such that we know them, they are valid in one direction. Then with connectedness, those theorems will be valid for, let's say, 2 directions. Okay. Another thing we can consider it is we may ask, is the space simply connected or not? Okay, this question provides us a technique for distinguishing between the sphere and the torus, for example. And there is lots of results and consequences. We can use them in applications and in other parts of mathematics to depend on these information or to depend on these results. Also, another question is the space oriented? We can ask, is the space oriented or not? For example, we can say that the regular cylinder is oriented since it has 2 sides, while the Mobius space is not oriented. All of these details, all of these properties are investigated by the concept of topology. Now, one may ask, why do we need topology, and who cares about topology? In fact, let's consider those 2 questions and then see what topology will give us, or to know what is the thing that topology is concentrating on in a space. Question number 1, imagine you have a super stretchy and bendy pants or any other, let me say, any other piece of clothes. Can you turn those, or let me say, can you turn those pants inside out without taking your feet off the ground? Someone may say, okay, it's difficult, but if you will think in a large way, and let me say extreme way, to imagine that how much stretchy the pants that I have is, you may say, yes, we can do such thing. Okay, but you must leave your mind to think extremely that we have super stretchy such pants, then we can manage it. At the end, I can simplify this idea by the following way. Consider that you have a t-shirt. Okay, it's the same t-shirt. You will wear it while you are, let's say, 55 kilograms, and then you can wear it while you are 70 kilograms. It's the same t-shirt, but when you are wearing it, it has a properties which is different in 55 kilos than, let me say, when you are wearing it as 70 kilos. It's the same piece, but different, different shape, different behavior, but at the end, it's the same. So the difference between the two cases is something which is depending on which properties in each case this t-shirt has. This is the thing that we are concentrating on topology. Okay, we may go to the second question. If you have a picture frame as here, okay, and you have this picture hanged with a string, okay, and you want to hang this frame using those two nails, okay, such that in a way such that if you release one of them, the other one will be by default released. Can you do such thing? The answer is yes. I don't know if you can follow the graph here. You may reach it.
Me, Doctor. Sorry to interrupt. The slide is not moving.
The slide is not moving?
Yes, it's still in the first page. Have you changed the slide or not?
Yes, I changed. I have a picture of a frame hanged somewhere. No?
In my screen is not moving.
Okay, let me try. Now?
No, not yet.
I don't know what's the problem. What about now?
Can you close and then restart sharing the screen again?
Okay, I will.
Use the slideshow.
Yes, I'm using the slideshow. Now?
It's just the first page.
No, it is the second page. I don't know what's the problem, but I will repeat again. I will stop sharing the screen and show it again.
Don't use slideshow, use the small one.
Okay, what about now?
Yes, okay, now. Change.
Okay, let's not use the screen.
Yes.
The slideshow. Okay.
Okay.
I was talking here. Okay. Oh, let me just. Okay, I was talking about this question. Like, imagine if you have this frame, okay, and with this string, and you want to hang up this frame using those two nails. The idea is, the question is, can we hang this frame by a method such that releasing one of those nails will by default release the other one? The answer is yes. I don't know if you can follow up the graph here or the shape of the hanging. The idea is it's at the end the same string, okay, but we are changing its shape, and depending on this we will have in each case different properties, and those properties are our aim to distinguish and to learn and to know if we have such property, what do we have consequences on the other hand. Okay. Can you see the slide now?
Yes.
Hello.
Yes.
Okay. And the idea is we will do something, we call it abstraction. Okay. This abstraction, we will start with ideas that we know from, let's say, real analysis, and we will start by enlarging those ideas and extending those concepts, extending those definitions to have something we call it topological spaces, okay? We will use, as I said, the abstraction. In fact, topology is very related with, let me say, algebra also. We will use lots of the concepts from algebra, and we can also say like we have a part of or a branch of algebra and topology, which is a mixed branch algebraic topology, which join theorems and concepts from topology and algebra. Over here, this is just an example of abstraction. What is the meaning of abstraction? For example, let's consider the following theorem. It is the extreme value theorem. As you know, we have, if we have a function f, which is continuous from a closed and bounded interval to R, real valued function, this function f achieves its maximum and minimum in the interval AB. This is a theorem that we used to take it in calculus courses. If we have a continuous function on a closed bounded interval, then for sure we have maximum and minimum for this function. If we will try to think widely, we can extend our theorem to the following one, okay? If we have a continuous, the second theorem says that if we have a function which is continuous from C to R, okay, it is a real valued function, continuous real valued function from a compact set, and later we will know what's the meaning of compact set C, then f achieves its maximum and minimum. In this case, the first theorem is considered as a special case of the second theorem, and the second one can be considered as a generalization of this first one. If we want to think more and more wide, we can go to the third one by considering the function f as continuous function from a compact set to a topological space X, not to R. In fact, R is a topological space, as it is, as we know it, as we deal with it in all mathematics courses, from simple to complicated. R is a topological space. Instead of considering R as a topological space, we will consider any other topological space to be my range of the function that I'm working on. In this case, we can conclude that the image of f is compact. The image of f is compact. The third theorem is a generalization of the second one, and for sure generalization of the first one, and each one of the first and the second theorem is a special case of the third one. The idea is, see, we replaced R by topological space. We replaced this closed and bounded interval in R by compact set. This means, or this gives us idea that we will extend the meaning of, let me say, closed and bounded, for example, to another concept, which is, which will guarantee the thing that we know, guarantee the truth of the thing that we know, and will cover new cases and new concepts for us. This is these three theorems, and the way how we go from the simplest case to the most general case give us an idea about abstraction and how we will work through the introduction to topological spaces from the analysis course, especially from the metric spaces. Okay, let's go to the next. So, by the way, they keep the same thing that I use for the second. Okay, then. Now let's introduce the metric spaces and open sets. What is the meaning of metric space? In fact, metric space is a pair X and D, while X is a set and D is a distance function. Set with distance function between each 2 points of the set X. We can define sets in the following way, as it is a function from X cross X, or the Cartesian product of X and X, to R positive. This means that our distance function must be positive, must give us a positive, let me say non-negative distance, okay? Such that the following 3 conditions holds. The first condition, the distance between any element and itself must be 0, and the distance between any 2 different elements is greater than 0, okay? This is the first condition. The second condition is the symmetric property, which means the distance between X and Y must be same as distance between Y and X. It doesn't matter from where to where should I take the distance. The distance must be the same in all cases. The third property is the following property, which is the distance between X and Z is less than or equal the distance between X and Y plus Y and Z, which we call it triangle inequality. Simply, we can consider those 2 points as X and Z, okay? Let me... Okay, let's consider this is X, let's consider this is Y, or let me say this is, for example, Z. If I will take the distance between X and Z, for sure it will be less than or equal the distance from X to Z, and then to go in another step to Z. This is the triangle inequality. It's very familiar and we use it in lots of places. Okay, in fact, if we look at those 3 properties, we can say easily that we have those 3 cases valid in the real numbers that we are dealing with in all mathematics courses. Let's consider this as the real line. Let's consider this to be 0. For example, let's say this is X. It's very clear that the distance between 0 and 0 is 0. It's very clear that the distance between any 2 different elements will be greater than 0. It is very clear that the distance from 0 to X is same as the distance from X to 0. It is also very clear that the distance between X and 0 is less than the distance between X and 0 by 2 steps, or more than 2 steps, let me say. We can do this by the following. In fact, we have more than one case for this, but let's just consider one case. Let's consider this is to be Y, and if we want to go from X to 0, I may go directly. This is the smallest distance. If I will go to Y and then to 0, this will be a greater value. In fact, as I said, there are more than one case depending on the order of those limits, but those points, but we just mentioned one of them. All of the other cases are guaranteed. This means that our set of real numbers is a metric space with the distance that we know it, which is just the absolute value between the 2 numbers that we have. So from the beginning, we are dealing with a metric space, which is R with the distance function, which is the absolute value, but we didn't mention every time that this is a metric space. So now we did something, some kind of abstraction. Okay, let me go to the next. Let's consider now the following examples. the vector space R to N, the vector space R to N is as an example of the metric spaces by having the Euclidean distance, which is something we know it, we deal with it or in lots of fields also, by considering the distance between x and y to be the square root of the summation of the distances between the elements of x and y. For example, if we have x to be x1, x2, up to xn, and we have y to be y1, y2, up to yn, then the distance between the Euclidean distance, let me say, between those two elements x and y will be the square root of the distance between those squared plus the distance between those squared plus until the distance between those squared. In fact, we have Rn over here. Okay, what if n is 1? This is another abstraction, be careful. What if n is just 1? Then we will have just R. Then the distance will be the square root of R n equals to 1. It means just we will have this x1 and y1. So the distance will be the square root of, let me say, x minus y, okay? All of it square, okay? And if we cancel the root with the squared, we will get something which is x minus y, which is the absolute distance that we mentioned before, like few minutes. And if n is 2, so it will be something which is the distance will be the square root of x1, let's say, minus y1, all of it square, plus x2 minus y2, all of it square, which is the distance between 2 points in the plane, which is something familiar, and we use it in even pre-calculus courses. It seems that we were dealing with metric spaces from the beginning, but we were not mentioning that this is a metric space. This is the idea. This is the thing that we are doing. We are doing abstraction, extending of the skills that we have to something which is wider. Okay, another example, let's consider this one. And by the way, over here, you can consider n as much as you wish to be. Let's the second example, let y be R to n, then y becomes metric space under the induced metric. In particular, we define metric y by simply restricting the metric space, which is y cross y. In fact, this is just generalization of the metric space for one space and then for the Cartesian product of it. Let's just concentrate on another case, which is simple and very important to mention here, which is this one. In fact, for one set X or R, how many metric spaces can we have? In fact, we can have lots of metric spaces for the same metric space. Now, something which is very important, we may mention it here. For example, if we have the plane and we want to find the distance between 2 points on the plane, for sure the distance will be straight line. Let me say the shortest distance will be straight line. But for example, if we have 2 points on the Earth, okay, is the straight line still the best way to find the distance between those 2 points? For sure, no. So we need something else to define the distance rather than the absolute value or the distance or the Euclidean distance which is given in the first one. That's why we need sometimes to define different types of topologies, different types of distance functions on the same space. For example, here On Rn also, we may define another metric space, which is the infinite metric space D infinity. It gives us the distance between any two x and y by the maximum distance between their elements. Let's go back above here. The distance, the D infinity in this case, will be the maximum distance between those elements, okay? The maximum distance between the corresponding, for example, if this distance is the largest one between those elements, so this will be my D infinity. For example, let's consider, I will ask a question. Let's consider R3, okay? Let's consider that x equals to 1, 3, 7, for example, and let's consider y to be 3, okay, 10, and 5, let's say. The distance or D infinity between x and y equals to. Who can answer such question? Hello?
Okay.
Hello?
Students, yes.
Yes, students, who can
And
answer? Who can take the
example?
challenge to answer such question?
You have x and y. So what is the D infinity?
D infinity, which is the distance between x and y, will be the maximum difference between the corresponding elements. So if you look at 1 and 3, the distance, the absolute value or the distance between them as real numbers is just 2. And the distance here is 7, the distance here is 2. So for sure, this will be 7. So the infinity between x and y will be 7 in this case. But if we consider the distance, the Euclidean distance, you will have different value for it. And with any new metric space or with any new distance function, we may have different value for it.
So it has to be with the same, in the same position. The element in the same position. Yes. So the students answered 9. So.
Oh, 9. So I said corresponding. I was mentioning that the corresponding elements, see over here, this yi and xi.
Yes.
They must be the same. Okay. Okay, let's go now to the third case. We also can define another metric space, which is just the summation between those corresponding elements, just the summation, and that's it. This means if we want to find D1 between x and y that we have over here, we may take 1 minus 3 or 3 minus 1 as absolute value of them, or the absolute difference between them. We will have 2 plus the difference between 3 and 10 is 7, and the absolute difference between 7 and 5 is 2. So over here we may get 11. So D1 between x and y is 11. Depending on the definition of the distance function, we may have different value for the distances between the same points in the same metric spaces. If there is any question, feel free to ask. Okay. We may go ahead.
Do you have any question? No, at the moment.
Okay, we may continue. Now we will define the open sets in a metric space. Now, if I asked you, what is the open set in R, let me say, in the real numbers, which are the just real numbers that you are dealing with in all courses. What is, or give me an example of an open set or open interval, let me say. Anyone?
Anyone?
Okay, I may give
open
you
set in R1.
Yes, Muhammad.
For me, is open set is a set of number without boundary. without boundary. With if circle, the open set of the circle is just the inside the circle, but without
without the
its
boundary.
boundary.
Great, that's great. You gave me more than I asked. I asked you to give me an open interval in R, which is, you said that it is the interval without boundary, which is, for example, we can consider 0 and let's say 3. This is an open interval in R. And you gave me also in R2, which is the circle, open circle. You said it will be all of the points inside the circle without the boundary, okay, which is also true. Now, these are, as we said before minutes, that's the real numbers, the set of real numbers with the absolute distance can be considered as a metric space, and also the R2 with the distance that we defined before is also can be considered as a metric space, but they are not the only two cases. We have lots of other cases of metric spaces. We need now to enlarge or to extend those things that you, Muhammad, told us about, to extend them to general case that can be considered in all metric spaces, not just in those two special cases. Those generalizations will keep the same meaning that we know, and nothing will be different for us. Even if we will call R as a metric space, all of the things, all of the concepts that we know will remain the same. This is the benefit, and this is the interesting thing of extending the small ideas to a larger ideas. Okay, open sets in a metric space. As you know, we have distance between 2 points. Generally, we can define the open sets by knowing something else, which is that we will depend on it to define the open set in late points. At first, we need to define something, we call it a ball of radius r centered at a point. Okay, so now we will define a ball B of radius r around the point x, or centered, we can say centered at x, which is given in the following way. This ball is consisting of all the points in the space x, or in the metric space x, okay, such that the distance between those points y and my center x less than r. If you look at it for a while, you may think like this is okay, this is the definition of the circle in the plane, and this is also the definition of the interval. If you look at our interval here, for example, this interval is centered at 1.5. okay, so all of these points here, if you will take the distance between them and the point 1.5, okay, let me change the example such that to have different radius than the center itself, to be clear when I am mentioning. Okay, this is 3, this is 1. This is an open interval, this is the center 2. If you take any point over here inside the interval and you take the distance between it and the center 2, you will find that this distance is less than or equal to 1, which is the radius r. We call it radius, which is r, that is mentioned here. So this is a ball, okay, of which we can describe as y belonging to r, okay, such that the distance between 2 and y less than 1. Okay, this is an open ball in R, okay, and it is working still under this definition. And over here, if you look at this is the circle, which is a ball in the metric space R squared. So if you take any point inside this circle and you find the distance between this point and the center, you will find that this distance is less than the radius itself, which is this one. Okay, so this is working still for our case or our earlier case of numbers, and we may extend it. It will be working for all of types of metric spaces also. Okay, we may go ahead. Okay. By the way, this ball, we can call it open ball because we are not considering the points with radius or with distance equals to the radius. It is an open ball. Also, we can consider it as neighborhood. We can sometimes call it as open neighborhood. Neighborhood for what? Of the point, which is the center itself. A neighborhood for the center. Okay. Okay, we may consider now the following definition, which is the definition of open set generally. Okay, the definition of open set generally. Consider the set that we have over here. Okay, consider the following set that we have over here. Now, if we want to check or to define an open set generally, which is, for example, U, this is U, okay, which is this one, and up to the end, you may consider it. This set can be considered or can be, yes, considered as an open set if for every point inside this set, we have an open ball around this point, okay, such that this open ball is entirely inside my set. Again, I will repeat. Consider that we have this set, which is U. This set is an open set if for every point here inside, and for every point inside this open set U, there exists epsilon, such that I can consider an open ball around this point, such that this open ball is entirely inside my set, which is U. This set, in such case, if this condition is hold, this set can be considered as an open set. Roughly, we can say that we have a safety margin such that for all of the points, we have a small neighborhood around it, such that this neighborhood is entirely inside my open set. And this idea can be also very clear if we consider the interval 0, 1, for example. And if I asked you what is the greatest number, sorry. If I asked you what is the greatest number that you can mention for me inside this interval, no way. You will start adding, and no way to reach the end. So always we have a safety margin on the borders from right and left. This means that our interval is an open interval, or our set can be considered as an open set. Okay, if there is anything you want to ask about, feel free to ask. Okay, let's go ahead then. Okay, we have some properties of the open sets or open ball. Generally, any open ball can be considered as an open set. This is something which is trivial. Any open ball can be considered as an open set. For example, and the proof of this thing can be also given easily in the following manner. Consider that we have this open ball centered at X with radius equals to R. Okay. Consider that we have this open ball, and you know this is not included. The boundary is not included. Okay, then how can I show that this ball is an open set? It is an open ball, as you see. How can I show that it is an open set? It will be an open set if for any point here, okay, for any point here, for example, let's call it C, this point must have a neighborhood, okay, with radius epsilon greater than 0, such that this neighborhood is totally inside my ball. Okay, then this is C. The thing that I will do, I will check which distance is smaller. Is it the distance between C and the center, or between C and the borders here? Okay, or simply you can say to this point C is closer to which side, to the center or to the borders outside. Okay, if it is, as you see in our case, closer to the border, okay, you will take half of the distance between the border and the point and consider it as neighborhood, and this is for sure completely inside the circle. And in the other case, if the point is inside the circle and let me say inside the ball and closer to the origin or to the center, take half of the point of the distance as epsilon, make a neighborhood, and this neighborhood is totally inside our ball. So this is just let me say a draft for the proof of this case. The property 2, phi is open. Okay, we can consider it as by default phi is an open set because like it can be considered as a special case, which is a standard case that we will use later. X is also an open because it contains all of the open balls for all of the points inside it. That's it. Simply, we can mention it like this. So phi and X are always open. And the property 4, the arbitrary union of open sets is open, even infinitely many. This follows easily from the definition. Over here, we can also consider this property. It is an important one. The union, even the infinite union of the open sets is also open. But for the intersection, we must have finitely many open sets to guarantee that the result of this intersection will be open. Okay, we can have example over here. See, over here we have the intersection of, I mean, this is, we can consider it as a counter example for this case, that we may have infinite open sets, okay, and the intersection of them will be not open, which is maybe closed or not open, not closed at a moment. Okay, let's consider this case. For our case here, we may consider this is 0. We may consider this is 1 over n. Okay, so 1 over n will be something like this. If we consider 1 over 1, it will be -1 minus 1, the -1 plus 1, then 1 over 2, then you will have half or minus half, then 1/3 minus 1/3, 1 minus 1/4, and you will start shrinking until you will be close to or let me close upon the 0 itself. So the intersection at the end will be the point 0, which is not open. All of these intervals are open, but because we have infinitely many open sets, at the end we got something which is not open. That's why we must have this condition over here. The intersection must be finite to get or to guarantee that this intersection is open at the end. Okay. we can go ahead. Okay, then. Okay, now we will introduce, or let me say, to remind you by the meaning of limits and closed sets. If we have over here, let's start with the definition of convergent sequence, or by considering the sequence P1, P2 up to Pn and so on as a sequence. This sequence is converges or convergent to a limit which is P if for all epsilon there exists some n such that for all n greater than n capital, we have the distance between those terms of the sequence and the limit point less than epsilon. Simply, we can explain this definition by the following way. Consider that we have this sequence P1, P2, P3, P4, P5, P6, until for here, let's say Pn capital. Okay, until reaching a step which is Pn capital. After this Pn capital, if it is guaranteed that the distance between all of the terms after Pn capital and a specific point which is P is less, I mean the distance is less than epsilon, whatever epsilon is, or how much epsilon small is small, then this sequence must be convergent. The behavior of this sequence will be as follows. As I said, this is 1, 2, 3, 4, 5, 6, 7, and then after Pn, all of the terms are concentrating in such a way, in this manner. So this means that our limit is convergent to that point. Okay, now let's consider the second lemma. If a sequence in a metric space converges to a limit, this limit is unique for sure. The limit of the sequence in the metric space is unique. Be careful that this lemma may not be valid if we go through the topological spaces. With topological spaces, we need an extra conditions to guarantee this result. Okay, later we will talk about it. And we have another definition over here, which is the definition of a Cauchy sequence. If we have a sequence P1, P2 up to Pn and so on in a metric space X, this sequence can be considered as Cauchy sequence if for all epsilon greater than 0, there exists a number n capital, okay, such that after this step in my sequence, all of the terms Pm and Pn, the distance between them is very small, which means it is less than epsilon. The meaning of this is as following. Consider that we have this P1, P2, P3, P4, P5, P6, and then I will reach Pn capital. After this Pn capital, all of the terms will be something which is like this. The distance between them will be less than the distance between any two terms will be less than epsilon, and epsilon can be as smaller as we wish. Okay, in such case, this theorem or this sequence can be considered as a Cauchy theorem. So this sequence can behave in the following manner, and then it can be just concentrating here. Okay, now there is a relation between the Cauchy sequence and the convergent sequence. In such cases, or in a specific spaces, both of them are equivalent. And generally, convergence implies Cauchiness, but the converse is not true always. Sometimes it's true. We need a condition, which is the condition of completeness. If the space is complete, then the Cauchy will implies the convergence. From the definitions, it's very clear that if we are approaching this point, so this means that we are all as terms, we are all very close to each other. So converging to one point, it means we are also very close to each other, which is the meaning of the quotient in this step. Okay. Oops. We may go ahead if you have no questions. Okay, then we can go ahead. Okay, this is the completeness. We have the following definition, which is the definition of complete metric space. The metric space is called as complete if the Cauchy sequence implies that this sequence is convergent. And something to take care about or to pay attention to, which is that the following: for any metric space, we have a larger metric space, which is a complete metric space. This means any metric space is sitting inside a larger metric space, which is complete. This metric space, we can call it X closure, or the closure of the metric space, which is consisting of the metric space X itself plus all of the limits points of the sequences inside the metric space X. Again, I will repeat. Every metric space is sitting inside a larger metric space, which is complete. This larger one, which is complete, is consisting of the basic metric space itself and all of the limit points of the sequences inside the basic metric space. Okay. We may go ahead. Okay. Something also to mention here that not all of the sets are either open or closed. Some sets are not open, not closed. Okay. Let me just check why I didn't mention yet the closed set. By the way, we can just mention it here quickly, that if we have a set A open, then A complement is closed. So the closed set is the complement of an open set. The set can be open, can be closed, and it can be also not open, not closed. So it's not either or just. Okay, let's go ahead to the next idea, which is the continuous function, to be able to start with the topological space soon. Okay, then. Okay, now we will just mention the definition of the continuous metric space, continuous function between two metric spaces. For example, consider that we have the following function f between two metric spaces x and y. Each one of those x and y has its own distance function. This means that we have for x distance x and for y distance y. This function is continuous if for all x's and epsilons there exists delta greater than 0, such that the distance between the points themselves in x is less than delta. The distance between the images must be also less than epsilon, must be less than epsilon. What does this mean? If we consider that we have, okay, this is x and this is y. If we have, for example, over here 2 points, okay, and the distance x and y, let me say, the distance between them is less than delta. If the function, which is defined from x to y, continuous, or the function f is continuous if, depending on the distance between x and y less than delta, the distance between their images, which is f of x and f of y, must be less than epsilon. Okay, this is the meaning of a continuous function, or simply we can say that the f of the ball centered at x with radius delta must be inside the ball, okay, centered at with radius epsilon centered at f of x. Okay, both of those two expressions are equivalent, and you may use any one of them. Okay, we have also here another theorem. A function f from x to y can be is continuous if and only if, for all open sets in the range, the pre-image or the inverse image of them is open in the domain. This is also another, it can be considered as a definition also for the continuous function from a metric space to another function, to another metric space. So simply we can say the inverse image of an open set must be an open. So in such case, the function will be continuous. By this, we have all of the concepts that we need from metric spaces to introduce the topological spaces. We may start now by defining the topological space. Okay, then topological spaces. We will define now the topological spaces. A topological space is a set with a topology. Metric spaces was a set with a distance function. Now we have a topological space is a space, okay, a set with a topology. Now, in the metric space, the distance give us a quantity, okay, a quantity which describe how much the 2 points that I am concentrating on close, okay? Now, in the topological space, we will have something we call it topology. This topology is a description of the open sets inside my topological, inside my space. That's why we call it topological, because we are depending on the topology. So the topology is a description of the open sets inside my space. Simply, we can just introduce it as follows. In details, we can say a topology is a collection T of P of X, collection T of P of X. What is P of X? P of X is the collection of all of the subsets, or yes, the subsets of the set X. There are open sets. These are open sets of X. T must satisfy. So a topology is a collection of subsets of X. Those subsets are the open sets. So the topology will pick the open sets from X itself. That's it. Okay? This topology must, or this collection must satisfy the following 3 conditions. The first condition, T must contain phi and X. This means that X and phi must be open, because T simply is the collection of open sets. Number 2, or the second condition, if ui belonging to T for I equals to I, then the union must be in T. This means the arbitrary union of open sets are open. This is a previous property, and still we are we have this condition in the topology. Third condition is the finite intersection of open sets must be open. So we have 3 conditions. The first condition is phi and X must be open. This means phi and T must be inside my topology. the union of the arbitrary union is of open is open, and the finite union of open must be also open. In such case, we put a definition, or we put a base for the open sets, and depending on this we can define closed sets, we can define also continuous functions, we can define limit points, boundaries, interior points, closures, and all of these concepts will be we will be able to define them depending on the definition of open sets that T chose them for us. We have over here another definition: a subset Z of X is closed if X minus Z is open. It's the same definition. It is it's easy to prove the following propositions. Okay, before going to the proposition, I will just mention here is a very simple example for a topology. Consider that we have X to be A and B and C. Okay, let me consider that my T is a topology. I'm considering that this T is a topology. So this means that phi must be inside the topology, X must be inside the topology. I may consider that A is another set which is open inside my topology. I will consider B also. And for sure, I must consider the AB because their union must be valid inside my topology. I may define this topology, which is T, by considering that phi and X and A singleton A and singleton B and AB, all of those are my open sets, and this is topology. Yes, if you want, we can check all of the three conditions that we have. The first condition, phi and X must be valid. Yes, phi and X, they are here. The second condition, the union, the arbitrary union, must be inside the T. Let's consider a union of phi and X is X, which is inside T. Union of phi and anything else will be the same thing, which is again inside T. Union of X and any other set will be the same as X, which is still in T. If I will consider union of A and B, it will be AB, which is valid. If I will consider union of A and AB, it will be AB, which is valid. If I will consider union of B and AB, which is AB, valid inside tau again. So it is a topology which is defined on the set A, B, and C. Simply, this is a very simple case of topological space. So we can now say that X and T, or X and tau, is a topological space. Okay, what are the open sets in my topological space now? The open sets are phi, X, A singleton, B singleton, and AB. What about the set B, C? Who can tell me now? Consider that this set to be, let's say, B capital. I am asking, is this set BC open or closed in my topological space? Anyone can answer such question?
Can anyone answer? Is the set BC an open set?
In fact, it is not an open set because it's not one of the members of tau. Simply, this is the answer. If this set B is a member of those 5 elements inside T, it will be open. Otherwise, it's not open. Now, if it is not open, is it closed? Not directly. You must check something else. For the set, depending on this theorem, for the set to be closed in the topological space, its complement must be open. This means its complement must be inside tau, or an element of tau. What's the complement of B, guys? B complement is just A. Is the complement of B open now? Yes, it is open. It is here. That's why I can say that B is closed.
Closed.
That's it. Okay, then let's go ahead to the proposition that we have here. In fact, we have correspondence between those three conditions of the topological space and three similar conditions for the closed sets in the topological space. This means that we can consider if phi and x are open, so their complements are closed. What's the complement of phi? It is x. What's the complement of x? It is phi. This means that phi and x also closed. So starting as a starting point, we can say like phi and x is closed. Both of them are closed and open at the same time. And keep this information in your mind. We will need it later. The second condition, which is the arbitrary, the arbitrary union of open sets are open. This means the arbitrary intersection of closed is closed. If you will use De Morgan's law, you may find this result easily. And depending on the third one, if we have the finite intersection of open sets, okay, if you have like, for example, finite from I equals to 1 up to n of open sets, let me say F, this is an open set, okay? We said this is an open set. What about its complement? Its complement will be using De Morgan's law, union F complement. These are closed since each F is open. So all of this is just closed. By using De Morgan's law, we can also send this 3 to the third case, which is finite union of closed are closed. If you have any question, you may ask before going to the next. So now in the topological, yes, doctor.
The tau, why not include the singleton C in your?
Again, please.
The tau that you,
yes.
The topology, yeah. You didn't include the singleton C.
Inside tau?
Yeah.
No problem. You can choose anything, any collection of subsets of X such that the three conditions over here hold.
Satisfied.
There's no need to include all of the points.
Okay.
Within few minutes, few seconds, let me say, we will have also another examples for these cases, and we will mention them. Okay, let me. No, I don't want this. I want this now. Okay. These are examples for topological spaces, and they are, in fact, very important cases, and we depend on them to explain and to understand lots of concepts later. The first one, the first topology is the indiscrete topology, or sometimes we call it the trivial topology. It is just consisting of two sets. Yani tau is consisting of just phi and x, whatever x is, even if x is all of R, or even if x is containing infinitely many elements, we can consider the topology which is consisting of phi and x only. And this is the simplest topology that we can build on a set. For all of the sets, we call it the indiscrete topology. And in fact, this topology is connected with the indiscrete metric spaces, and it is connected with the indiscrete function, which is giving us the basic of lots of other applications in lots of other fields. This is a very basic case. If you want to check the three conditions that we have, okay, phi and x valid. The union, the arbitrary union is open, and the finite intersection is open. By default, we just have two sets, and intersection of them is phi and union of them is x. Both of the results are valid in tau. This is the simplest topological space that we may define. We also can consider the discrete topological space. The discrete topological space, in fact, is the largest topology that we can build for a set, which is consisting of all of the possible subsets of any set x, which is the power set of x. See, it is consisting of 2 to x, which is the power set of x. In fact, in the indiscrete, the only open sets are phi and x. But in the discrete case, because all of the sets are valid inside tau, this means that all of the sets, any set that you can imagine, is an open set. Okay, any set, whatever the set is, it is an open set. Okay, let us just give example for the discrete case to our previous case, which is x. We had a, b, and c. Okay, I want to write the discrete topological space for this set. In fact, for every set, we can define the indiscrete, the discrete, the particular point, the excluded point. All of these examples, we can define them for every set. Okay, I want tau. So tau will be consisting of all of the possible subsets of x, which are phi and x. I will start by them. Then the singletons A, B, C, and then I will take the subsets by two elements, which is AB and AC, BC. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Yes, we are done. 8 elements. And as you know, in the power set of any set, it's consisting of 2 to the power n, which is the number of elements. 2 to 3 is 8. And we have 8 subsets. All of the possible subsets of x are given in tau, and this is the discrete space. Now, if you look at those sets inside tau, you may see that all of the possible subsets are open. Any subset of x will be open. Even any subset is closed. How? Okay, because the complement, for example, of BC is just A, which is again here, which is open. This means it is closed. And the complement, because A is open, the complement of A is BC, which is closed. So every subset of the discrete topological space is open and closed at the same time. But in the case of indiscrete case, the only open sets are just x and phi. This means no open sets rather than x and phi, which means no closed sets rather than x and phi also. Okay, is it clear? Okay, then we can go to space 3. We can go then to space 3, which is particular point topology. We can define also a specific type of topologies, which is particular point topology. How do we define it? We define it in the following manner. We take all of the subsets that contains a specific point with phi and x. Okay, so this is the definition of it. So the definition of this, we can consider to be tau or t. It is consisting of phi and x union all of the sets, all of the subsets of x containing this point, all of the subsets of x containing these points. By the way, because this tau here is consisting of all of the subsets of all of the possible subsets of X, we can define the topology, the particular point topology, for the same example. For example, I want TA. What does that mean? It means I want to define the particular point topology on X, which is given here, such that my fixed point is A. It means I will take everything. At first, I will take phi and X with everything containing A. Where is A? Over here, I can find A. Over here, I can find A. And
B.
over here, I can find A. So it will be consisting of A and AB and AC. That's it. So this is the fixed point topology, or sometimes we call it particular point topology. On the other hand, space 4 consisting of excluded point topology, which is consisting of phi and X union all of the subsets that are not containing S. For example, if I want now T prime, let's call it T prime A, which is the excluded point topology of this, will be all of phi plus X with everything not containing A, which means I will take B and C alone, each one of them alone, and BC together.
BC.
Yes, so this is the excluded point topology. So as you see, we are defining more than one topology on the same space, which give us different aspects and which give us different method to define or to describe this space. In each case, we have a specific properties valid or not valid in the space itself. But over here also example number 6, which is the cofinite space. The cofinite containing all of the subsets such that their complements are finite. Okay, all of the subsets of X such that the complements are finite. Union, of course, union phi, because phi must be valid from the definition at the beginning, so we will add it by default. In our case here, as X is given as ABC, it is finite, so any complement will be finite. We may consider R, okay, with this topology. Let me say, call it T star. If I want to give example of an open interval in this topology such that the complement of this open set must be finite, we can consider from minus infinity, that the set A from minus infinity to, let me say, 1, union from 1 to 3, for example, union from 3 to infinity. Okay, this is A. If I check the complement of A, it will be 1 and 3, which is finite. Okay. So the topology, the cofinite topology on R will be consisting of all such sets, such that the complement of them will be finite. This is an example for the cofinite space. In fact, we have also Sierpinski space, which is a special case. It is defined on a space of 2 points, okay? And we consider the space to be phi, and one point of those 2 points, each one you may consider A or B, and X itself. This is AB, which is X. This means that phi is valid, X is valid, and one point of those 2 points that our X is consisting of. By this, we mentioned lots of cases or lots of examples for topological spaces. We may go ahead.
There is a question. You want?
Yes.
You will answer now or later?
Now, why not? Yes, now.
If a set can have more than one topological space.
Of course, yes. We mentioned Yes, this is the example that we were working on. We gave the
X,
example,
yeah.
which is the set X equals to A, B, C, and we defined more than one topological space on the same set. Each case will give us different properties for the space. Well, however, if we will take the first as example, if we took the space one, which is the indiscrete, there will be no open sets rather than X itself. If we took it with the discrete, the exam space 2, which is the discrete topological space, everything will be open, everything will be closed. So you see, for the same set, different topological space will give us different aspects and different properties for the subsets inside it. Any other questions?
That's it for now.
Okay, then we can go ahead. Okay. In fact, we have an example over here. Find a topological space, which is X and phi, or you may call it tau. I prefer always to use tau for the topology, with a set A, subset of X satisfying all of the following properties. The first property is A is neither open nor closed. I told you before that not all of the sets are either open or closed. Sometimes it's not open, not closed. A is the union of an infinite number of closed sets, okay? And A is intersection of an infinite number of open sets. The answer is the interval 0, 1, closed from the side of 0, open from the side of 1 in R. Now I will show you how this interval guarantee or guarantee the three conditions above. For example, this is 0, or you may consider any other interval, one-sided closed, one-sided open, and you may work on it. At first, it's very clear that such interval is not closed and not open in R. Okay. By the way, the R, the real numbers that we were dealing with all of the concepts that you know is a topological space. We call it Euclidean topological space on R. It is a topological space. So we will be dealing with those things as we are dealing with the topological space. Okay, this is not open, not closed. It's very clear. I want it to be union of an infinite, okay, number of closed sets. Okay, so if we consider that my interval I is the union of minus 1 over n, okay, and 1 minus 1 over n, okay, as closed. This will be the following. I will explain it by by the graph itself. Sorry. So minus 1 over n will be something here, somewhere here. And if n is increasing, so we will be getting closer and closer to the 0 from the left side. At the end, we may say, okay, we will reach 0, but from the left side, so 0 will be included. From the other side, or the right-hand side, 1 minus 1 over n will be something which is here, okay? And by increasing n, the fraction 1 minus n will be decreasing, and we will be getting closer to the 1 by 1 from the left side. So 1 will be excluded. We will not reach 1 as we want. So it will be from the one side open. So by this, we showed that it is a union of an infinite number of closed sets. Let's go to part C. A is an we want A to be an intersection of an infinite number of open sets. Intersection, not sorry, this is for the intersection of open sets. I will do the by the way, on the same graph, we may consider the intersection of infinite number of open sets if we consider the open sets, this one, which is 0, okay, intersection 1 over n, 1 over n, 1 over n, and from this side, you may consider also the, let me say, we can take any point here, let's say half, plus n, plus 1 over n. Oh, no, it's not working by this. Okay, let me check it again. Intersection of infinite number of open. Okay, we may consider the one itself here as open, and we may consider the minus 1 over, just 1 over n in positive. Okay, those, as you see, 1 over n and 1, each one of them is an open set. The one side will be always open and constant, and this one, 1 over n, it can be here, 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 and you may go until you will reach the thing that you wish. By this, we will be able to demonstrate the thing which is asked in the question. And we may go ahead. Check the time. Okay. Oh, okay. I will try to go quickly a bit. Okay, then now we will define something, we call it or something which will let us be able to order topological spaces. Definition, we say topology T prime is finer than T if it contains more open sets than T, namely if T is subset of T prime. Okay. This is a way to order topologies. For example, I will explain the ideas simply in the following example. For example, let's say we have A, B, C, which is the example that we mentioned before. If I consider tau 1 to be x and phi and A itself, I may consider tau 2 to be x and phi and A itself with AB. Okay, those are two topologies. If you look at tau 1 is a subset of tau 2. So in such case, I can say that tau 1 is finer than tau 2. Okay, the idea is not always we can order the topology or we can compare topologies. Sometimes I may have tau 3, which is, for example, x and phi and B itself. Okay, and this tau 3 is not comparable with tau 2, and even it's not comparable with tau 1. So not always we can compare two topologies. Okay, sometimes it's possible. If it's possible, we compare them in the previous manner that we mentioned. And something to say here is that the simplest topology that we can define on any set is the indiscrete topology, consisting of x and phi, and the largest topology that we can define is the discrete topology, which is consisting of all of the or the power, let me say the power set of x itself. All of the other topologies are sitting here between them in a middle case, let's say, between the indiscrete and the discrete. Okay. We may go ahead. Okay, now we will define something, we call it basis of a topological space. Okay, a basis is a collection of subsets of the set itself, X. Okay, such that B covers X. This means X is a subset of all of the union of all those B. Okay, And if we have two elements in the basis, then their intersection must be again in the basis. Okay, so if we have a collection, for example, of B1, B2 up to Bn, for this set to be beta, let's say, to be a basis for a topology, the union of those B's must be covering X itself, and the intersection of each one of those two elements inside beta must be again inside the basis itself. Over here, we can also define or introduce the meaning of when the topology is generated by basis. Generally, we can say a topology T is generated by a basis B. This means that for each open set, okay, for each open set inside the topology, my basis or the basis that I have must has element inside my open set. Okay, again, I will repeat, for a topology T to be generated by beta, okay, any open set, let me say U over here, must contains here basic elements inside it. Over here, we can say that a topology which is generated by any basis guaranteed to be topology and to be all of the conditions of the definition of topology must be valid, or they will be valid by default if we will build the topology depending on a basis, or generate a topology depending on a basis. Let's now introduce this is the way how we generate a topology using a basis. If we have a basis which is beta, then the generalized or the generated topology tau using beta, consisting of all of the possible unions of those open sets or all of those betas that we have. All of the possible unions will give me a topology. This topology, we call it the topology generated by this basis. Okay. And then what do we have? We have a subspace topology. A subspace topology. A subspace topology is a topology which is defined not on the set X itself. It is defined on the set A, which is a subset of X. Simply by a simple example, we can explain the idea. Let's consider X to be, let's say, 1, 2, 3, 4, okay? And let's define tau to be X and phi and 1 and let's say 2 alone, okay? This is 1 and 2 and 1, 2, okay? This is tau. Now, if I want a subspace topology, we give it the symbol TA. What is A? A is any subset that you want. You may choose it from X. I will choose my A in this case, for example, to be 1, 3. Okay, this is A. So tau A will be the intersection of every element in tau with A itself. What is the intersection of X and A? It will be A. What is the intersection of phi and A? It will be phi. What is the intersection between 1, the singleton 1, and 1, 3? It will be 1 itself. What is the intersection of 2 and 1, 3? It will be phi. What is the intersection between 1, 2 and 1, 3? It will be 1. We wrote it and we are done. This is a subspace topology. We built it depending on the set A by making the intersection between the topologies, the original topology with the set A that we have. TA is indeed topology. It is very easy to show that TA that we built in the way that I showed you is a topology, and all of the conditions of topological spaces valid in it. Okay. Then we can go ahead.
Dr. Kinder? We have
Yes, Dr.
5 minutes.
5 minutes. I will try to go quickly through without examples. I didn't feel
Okay.
that the time passes quickly.
Okay, no problem. Okay. Yes.
Okay, I will try to go without examples by mentioning the. Okay, what do we have here? Let me just check. These are just examples of open sets in the topological spaces that we were dealing with them, which are the real numbers, the plane, even the sphere, all of the space. Let me say, all of them are just the topological spaces. A product topology, we can define the product topology by defining two topologies and consider the Cartesian product of them. If they are both topologies, then the Cartesian product of them will be topology. That's all. The idea is very simple. And if we have basis for one of them and the other, and we have basis for the other one of them, the Cartesian product for both of them will be a basis for the new topology, which we call it the product topology. The continuity here, the idea of continuity is simpler than in the metric space because we are just dealing with open sets, and the open sets are just defined in the topological space, and that's it. Without dealing with distances and epsilons, it will be easier. A function f is continuous if the inverse image of open set is an open. That's it. Simply, this is the definition of an continuous function. And also, as a result, we can consider that if a function is continuous, also if the inverse image of the basis is, and again, in an element base inside the inverse, inside the range itself. Also, we have another form for the continuity definition. Let us just consider those three cases. A constant function is a function which will give us a constant value, which is f of x equals to y0. It's always continuous in the topological space. And if we have a function defined on x itself, then the induced function also on the topological, the subspace topology will be also continuous. And if we have two functions that they are continuous, then the composition of them will be continuous. The closed sets and limits in the topological space, the closed set is a set such that its complement is open. Its complement is one part of the topological space. And we consider also here the definition of a closure. Closure of a set is the smallest closed set containing the set that we have. In fact, the definition of closure and interior and boundary, all of those definitions are exactly the same as definitions in the metric spaces, except that if we are dealing here with, we are not dealing with distances. We are dealing just with the building of the topological space rather than the distance itself. Over here, we have a definition, which is the density, introduced the density of the set. A subset A is considered to be dense if its closure is X. As example, if we have the topological space R, we have Q, which is the rational numbers. Q closure is R, so we can consider as Q is dense subset of R from a point of view which is topological, not just in we know this in calculus, we mentioned such property, but now we are dealing with it as a topological space. So we can also introduce it from a topological point of view. We can introduce also the interior points. Interior points are all of the points such that interior point of, let me say, a set X. This point is interior if we have a point, if we have an open interval, which is entirely inside the set A for any point X inside A. If such condition holds, then this point is an interior point. And also we have the boundary point. The boundary point is a point such that it is on the boundary, which means any neighborhood or any point, any open interval around it contains points from the point A, the set A itself and the complement of A itself. Let me. Okay, then what do we have else? Okay, limit points. Now the limit point, it is a point such that for every neighborhood, for every neighborhood, we will have, let me just try to explain it by graphing. It has the same meaning as the real analysis. A point X is a limit point of a subset A if for every neighborhood of this point there exists a point which is rather than the point itself and it is inside U. For example, over here, this point is a limit point, which means for every neighborhood around this point, I have another point from U or A, for example. I cannot separate this one. It is not a limit point if it is separated like this. This means with this neighborhood, I have no points of the set A. This means that it is not a limit point. Okay, we may consider also that the closure is consisting of the set itself and all of its limit points. If you look at the graph that I have here, this is the A itself. The limit points will be somewhere here. And then the union of the limit points and the points of A themselves will give us the closure, the closure of the set itself. Okay. At the end, we have also some properties for the topological space. One property is connectedness. We called a topological space as connected if it's consisting of, simply I will mention it, if it is consisting of one block, if the topological space is consisting of something which is like this, such that this one, such that both of A and B are open and the intersection between them is phi and the union of them will give me all of the metric space X. This means that my metric space, my topological space is disconnected. Otherwise, it will be connected. Again, I will repeat that the metric space is disconnected if it's consisting of two disjoint open sets A and B such that the union of them will give me my space X. Okay, and the continuous over here, something which is important, the continuous image of connected is connected. Okay, so the continuous image of connected is connected. Over here also, if X and Y are connected, then the Cartesian product is connected. Whatever we have X and Y or X1, X2 up to Xn, all of them will be connected. Another property which is compactness. The property of compactness depends on the open covers. A set, a topological. Oh, at first, if we have, for example, a topological space or a set inside a topological space, if we have, for example, this is open, this is open, open, open. As you see, the union of those open sets are covering my set A, let me say AB, or my interval AB. This is open cover. Okay, now if each open cover of the set A, B, or A, okay, has a finite subcover, then this set is compact. Okay, then this set is compact. For example, if we have the following interval, okay, and I have this with this, with this, with this, with this, okay, and then I have lots of things here. Okay, this is an open cover. If we remove all of these, and just keep those are still covering my set, and they are a finite subcover. In such case, we may have, if this condition is valid for all of the open covers that we have for our set, then we call it a compact set. And also we have a continuous image of compact set is also compact. In compactness, we guarantee that we guarantee that we have the I missed it. Okay, that we have the maximum and minimum in R, and also okay, let's just leave those examples. Okay, let me just concentrate on something which is familiar for you from calculus, even from elementary calculus. For example, if we have the set A and B in R, this set is closed and bounded. Okay, this set is closed and bounded. It has maximum and minimum. If the function is defined from A, B to, let's say, R, this function F has maximum and minimum. This function AB is a compact set in R. In fact, we have a very interesting theorem, which is Heine-Borel theorem, which says that in R, or let me say in Rn, closed and bounded intervals are compact. Also, vice versa, compact sets in Euclidean topologies is just the closed and bounded set. This is a compact set. Okay, if we have any open cover for it, we must have at the end open cover, open subcover from it. Generally, in other type of topological spaces, closedness and compactness is very related. Okay, and not always if we have compact, then it will be closed. For example, in R, closed with bounded space will give us compactness, and compactness also give us closeness. And for example, we can say like closed subset of a compact is always compact. This is there are such theorems that give us a special cases of these properties. Okay. Again, the Cartesian product of compact will give us compact case or compact metric spaces. Now, the general idea about topology is that topology is very abstract, which is true, but this does not mean that we don't have applications for topology. In fact, topology has applications in many branches of mathematics, okay, in other fields of mathematics. This is from the first aspect, and also there are some applications in another fields for like physics, computer science, networks, even business. There are some applications for topology in business. Over here, you may consider a simple example for topology in business. Simply put, network topology helps us to understand two crucial things. It allows us to understand the different elements of our network and their where they connect to. It shows us how they interact and what we can expect from their performance, and lots of details that may be mentioned in the applications of topology. Basically, it is an abstract, and it is started as very abstract, but by one, it has lots of applications and lots of uses in other types of sciences. Thank you for listening and for your time. And if you have any question, feel free to ask.
Yeah, it's very interesting lecture. We should have a part 2, I think. There's one question here in the chat box. Can we relate topological space to the error set in numerical methods? Can you understand the question?
Can we relate
topological space to the error set in numerical methods? You know, when you do
error set.
When you do numerical methods, you know, we calculate the error. So can we relate?
I think yes, by defining the by defining, but it must be depending at first by defining metric space, then translate it or then extend it to the topological space, because in numerical to find the error you need to define quantity, you need to define distance, you need to define or to calculate the error. If you want to do such thing, you may define the metric space and then go from the metric space to the topological space. After that, it's possible, but I'm not sure it will be effective at that moment. It may be, but as I told you, you must at first depend on the metric space to release to the topological space to be considering the distances and the errors.
Okay. So it's you generalize the distance.
Yes, you decide what type of error you want to use. You know that there is lots of types of error. Depending on this, you may define a suitable distance metric space, distance function. So the metric space will be defined, and then you can go to the topological space using the metric space. As it is, the topological space can be considered a general case of the metric space with some special conditions.
Oh, yes. Thank you, Dr. Kinda. Any more questions?
Thank you too.
From the lecturers, maybe, to teach functional analysis? I have a question. What about the concept of homeomorphism?
Homeomorphism, yes. Homeomorphism, it is a relation between two topological spaces, okay? The two topological spaces can be homeomorphism if there is a function, a continuous function. If you can find a continuous function with some conditions going from the topological space X to topological space Y, then having such a function will let us to say, like, okay, X and Y are homeomorphism. This is mathematically, and let me say in abstract way. But in another case, in another way, or roughly, we can say, okay, the example that I mentioned, which is the T-shirt example, like it's the same T-shirt, okay, but with different cases, with different shapes. It is the same, so they are. It is both of the two cases, they are homeomorphism. It means that they are the same, but with different topologies. Okay, we can say that they are very related. So we can define function which is continuous, for example, or let's say with some conditions. So they are. We can say that it is homeomorphism. By the way, continuous one-to-one and onto it must be.
Okay. Any more questions from the audience? This is from Berlian. We all know that learning math is not always easy. So is learning topology. So how, as students, how can we study abstract theory in math, like topology, in an easy way, easily? How can we understand it? Yeah.
I'm always telling my students, at first, feel like you want to study math with, I know maybe most of, with passion. This is the word, with passion and with love. If you will do such thing and you pay the time which is needed, for sure you will be okay with it. And always be careful that concentrate on the mathematical behavior of the statements that you are studying. Concentrate on the deep meaning and try, when you are studying, to change the symbols, to change the words, to change the frames that it is written in the textbook that you are using, such that your mind will be thinking in a large way. Whatever you will use later, the idea, the deep idea, the mathematical behavior will be stable and continuous in your mind. This is the way. And pay time. It's nothing without paying time. You must spend time working, studying, and practicing. That's it.
Okay, so the students, that is the advice from Dr. Kina. Thank you very much.
I thank you too.
Yes. So that, if I can wrap up for this wonderful lecture, you start from giving us the properties metric space, yeah, as the basic groundworking for the topological space. Let me share. I hope, please correct me if the summary is wrong. So topological spaces generally is a generalization of the Euclidean spaces, right, in which the idea of closeness or limits is described in terms of relationship between sets rather than in terms of distance. Okay. So topology studies spaces from qualitative perspective.
Yes.
It's an abstraction of the metric space. Yeah. Every topological space consists of a set of points, a class of subsets, which is defined as geometrically as open sets, and the set of properties of union and intersection. And lastly, I would like to share, I found this in the internet, about that topologies consider a donut and the cup of mud is identical. Isn't it true?
In such a way, yes. But sometimes it's not easy to imagine, like how a donut is same as that thing, which is a mug or something like that.
Okay. I found this in the internet, so okay, that was a joke. It's like a circle and a square. They say also, this is the homeomorphic
yes,
concept,
because
right?
they are closed. They are closed. Both of them are closed. I will just explain simply. Like they are you said triangle or rectangle?
Circle with a square.
Circle with square.
This
yes, I think they are homomorphism.
Yes.
Yes, because at the end they have the same thing. They are not. We all yes, we almost basically concentrate on connectedness. If we have something which is like switched, if the path which is inside the topological space will keep the same manner inside this and inside that. That's it.
Okay, thank you very much, Dr. Kinda. We give round of applause for her interesting, and we hope that benefit the students and motivate students to love topology. So this is the end of our lecture, visiting lecture program. I return back to the MC, Miss Aisa Sylvie.
Okay, once again, thank you so much, Dr. Kinda and Dr. Ratna for the lecture. It is a very interesting topic, actually. Okay, now next to the next agenda, let's all turn our camera on and put some smiles because it's time for some photo sessions. Once again, to all the participants, please turn on your camera and smile for some picture. For our to our operator, please help us to take pictures. Yeah. How many slides? One slide. Okay, there's only one slide, so I will count to 3. Please hold the smile. 1, 2, 3. Okay, one more time. 1, 2, 3. Okay, thank you everyone for the pictures. Okay, on our next agenda, there will be a lecturer certificate handover to Dr. Kinda. And for that, let us welcome the head of mathematics departments, the head of mathematics department of Diponegoro University, Dr. Susilo Haryanto, SSE, MSc, to hand the certificate.
Thank you, Sylvie. Assalamualaikum warahmatullahi wabarakatuh. Before we close, I will give a certificate to Dr. Kinda as a speaker at the visiting lecture program at the Department of Mathematics Diponegoro University today. I think the topic is very interesting and important for my student, although it is difficult but very, very interesting. Your explanation, this topic is very clear, and by this event, I hope my student increase the motivation to study hard, and I hope we will kita bisa kerjasama lagi di acara-acara berikutnya, gitu ya. And I think it is enough. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Yes, we hope that we can still collaborate later in the future. I hope you will be able to collaborate again next time.
Yes, thank you, Mrs. Ratna.
Yes.
Okay, thank you, Mr. Susilo, for the certificate. Now, ladies and gentlemen, we've finally come to the end of today's event. Once again, we would like to thank Dr. Kinda for all the knowledge that she shared with us today. And I would also like to thank all the participants who took the time to attend and actively participate on today's visiting lecture. Hopefully, today's lecture will be very beneficial to all of us. And I would also like to remind once again to all the participants to fill in the presence. It is in the comment section of this meeting. Okay. Finally, it has come to the end. I am Aisha Sylvia as the Master of Ceremony this afternoon. I would like to apologize for the mistakes that I might have made today. Thank you so much, everyone. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank
Thank
you very
you,
much,
Mrs.
Dr.
Kinda.
Kinda.
Thank you.
Terima kasih Bu Ratna. Terima kasih
Ya,
semuanya.
sama-sama. Ya, terima kasih juga pada panitia. Okay, Dr. Kinda, you allowed to leave the meeting.
Experience. Thank you.
You're welcome.